And this is section 7.4 where we are covering electric potential energy. But before I do begin, I need to go back and review one thing that we weren't able to get in the last section video because I went a little bit longer than I expected. So let us look briefly at a uniform electric field. And let's suppose in this case that we have two parallel plates. And on plate 1, right here, let's suppose that it has a total charge of positive Q. And these two plates are separated by some distance as well. And opposite charge, so the total charge on this plate is going to be negative Q. So we know along this plate at different points we will have positive charges and negative charges on the other plate as well. Because of these opposite charges and the law of electric charges, we know that there will be an electric field that exists between these two plates, and it will go towards the negative charge. And we use the field lines to show this. Leaving the positive charge, going away from the positive charge and towards the negative charge. So what this tells us is that our electric field is actually going towards the negative charge. So there's the direction in which it is going. And we call that our electric force, which is calculated by Q E. That electric force will be going in the same direction as our electric field. So the electric force also goes in the same direction as our field. And this field does work on the charge as it moves this distance Q. And that point really brings us in nicely to talk about electric potential energy. E subscript E. We are talking electric potential energy about the electrical energy stored in an electric field that can do work on a positively charged particle. Electric potential energy is also the energy stored in a system. Of two charges a distance delta D apart. So very easily, we know that our change in electric potential energy is going to be the negative work. Substituting in the negative work, or the work, sorry, that is, work is the same as our force multiplied by our distance, and in this case we have an electric force, so we can make that substitution. But we have a formula that we can calculate our electric force with, So our change in potential electric energy is negative QE multiplied by some distance delta D. And this gives us the change in potential energy through some displacement D. As a side note that we should just make sure we know, we use the sign of Q given to us since electric energy is actually scalar. So what might happen, or what does happen, if we have a proton that starts from rest in a uniform field and has a magnitude of 175 newtons per coulomb? Let us calculate the change in electric potential energy if the proton moves from those distances. So what actually are we given in this case? And it's going to be very clear how to solve this momentarily. We know that the initial placement or position was 1.45 meters from the origin, and that the final position was at 2.95 meters from the origin. So we know that our change in position is 1.5 meters by subtracting the final and the initial positions. We're given in this question as well the magnitude of the field being 1.75 newtons per coulomb, and we have a proton that's moving. The charge of a proton Q is 1.60 times 10 to the negative 19 coulombs, which we can easily look up if you need to, or just keep this memorized for future references. And we are going to calculate the change in electric potential energy. Which will be negative Q epsilon delta D. Making these simple substitutions to calculate the change in electric potential energy using a calculator, we get negative 4.2 times 10 to the negative 19. And I look at my significant digits quickly. I need 3 significant digits. So my change in electric potential energy is negative 4.20 times 10 to the negative 19. And because this is energy, the unit is in joules. So what does this answer really mean? I realized it paused again on me. So please go to part 2 of this video.